Hello, this is Professor Kuehn. Welcome back to my lectures on electricity, magnetism, and light. Today we're going to look at how Michael Faraday was led to the concept of the magnetic field by studying the iron filings around a bar magnet. This is recorded in Maxwell's lecture on action at a distance, which is included in a student's guide to the grade physics text, volume 3. We begin reading on page 387. This is titled Experiment on Lines of Force. In this experiment, each filing, so think about an iron filing, little ground up pieces of iron placed near a bar magnet. In this experiment, each filing becomes a little magnet. The poles of opposite names, north and south, belonging to different filings, attract each other and stick together, and more filings attach themselves to the exposed poles, that is, to the ends of the row of filings. In this way, the filings, instead of forming a confused system of dots over the paper, draw together, filing to filing, till long fibers of filings are formed, which indicate by their direction the lines of force in every part of the field. The mathematicians saw in this experiment nothing but a method of exhibiting at one view the direction in different places of the resultant of two forces, one directed to each pole of the magnet, a somewhat complicated result of the simple law of force. So he's referring to the push and pull forces that Ampere had conceived of as acting at a distance between magnets. But Faraday, by a series of steps as remarkable for their geometrical definiteness as for their speculative ingenuity, imparted to his conception of these lines of force a clearness and precision far in advance of that with which the mathematicians could then invest in their own formulae. In the first place, Faraday's lines of force are not to be considered merely as individuals, but as forming a system, drawn in space in a definite manner, so that the number of lines which pass through an area, say 1 square inch, indicates the intensity of the force acting through the area. Thus, the lines of force become definite in number. The strength of a magnetic pole is measured by the number of lines which proceed from it. The electrotonic state of a circuit is measured by the number of lines which pass through it. So the way that Faraday is thinking about this is if you have a bar magnet, let's say like this, one can draw these lines of force. And as we mentioned earlier in the class, these lines of force form closed loops. I'll continue them inside of the magnet like this. Try to draw this fairly symmetrically. I will try to draw them without crossing. It's a little bit tricky. Now, the nice thing about drawing these lines of force is, first of all, they form closed loops. So if this is the north pole of the magnet right here, and this is the south pole right here, let me do that in a different color so it's a little bit easier to see. So if this is the north pole of the magnet on the top and the south pole on the bottom, what is the magnetic field lines are coming out of the north pole and they're coming into the south pole like this. So each of these lines formed a closed loop. I'm not going to draw all of the arrows, but what Maxwell mentions here is that if you consider a particular region, like let's say 1 square inch, and draw a square inch loop right there, the strength of the magnetic field is related to the number of lines of force that are penetrating this loop. So you can probably see, if you're very close to the face of the magnet, there's a very strong magnetic field strength, and that's indicated by the large number of lines penetrating that loop, the large magnetic flux through that loop. Whereas if you draw the same 1 square inch loop out here, there are far fewer magnetic field lines penetrating that loop, and so there's a weak field at a larger distance. So drawing these lines of force gives you a graphical, if not mathematical, then at the very least graphical way of understanding the intensity of the magnetic field. And that's one of the virtues of this approach that Faraday developed. In the second place, Each individual line has a continuous existence in space and time. When a piece of steel becomes a magnet, or when an electric current begins to flow, the lines of force do not start into existence each in its own place, but as the strength increases, new lines are developed within the magnet or current and gradually grow outwards so that the whole system expands from within, like Newton's rings in our former experiment. Thus, every line of force preserves its identity during the whole course of its existence, though its shape and size may be altered to any extent. So what he's referring to here is that these lines don't have a beginning in space and an end in space. They're all closed lines of force. But as let's suppose you were to take an electrical current and pass it through a wire. So let's suppose we have a loop of wires like this. I'll draw a helical coil. And when there is no electric current flowing through it, there is no magnetic field that's created. But if then you turn on an electrical current flowing through this loop in this direction, then what happens is you get these lines of magnetic force that are formed, but when they form, they are immediately in closed loops. And as you increase the current, you're increasing the intensity of the magnetic field, and hence that can be graphically represented by increasing the number of lines of magnetic force, or the magnetic field lines that you are drawing. I have no time to describe the method by which every question relating to the forces acting on magnets or on currents, or to the individual currents in conducting circuits may be solved by the consideration of Faraday's lines of force. In this place, they can never be forgotten. By means of this new symbolism, Faraday defined with mathematical precision the whole theory of electromagnetism in language free from mathematical technicalities and applicable to the most complicated as well as the simplest cases. But Faraday did not stop there. He went on from the conception of geometrical lines of force to that of physical lines of force. He observed that the motion which the magnet or electric force tends to produce is invariably such as to shorten the lines of force and to allow them to spread out laterally from each other. He thus perceived in the medium a state of stress consisting of a tension, like that of a rope, in the direction of the lines of force, combined with a pressure in all directions at right angles to them. So this is an important step, is that these are not regarded by Faraday as merely mathematical conveniences or geometrical depictions. He's claiming that these actually exist, and these magnetic fields actually are exerting forces on other magnets. So this is different than the perspective of Ampere. Ampere's one of his main ideas was that unlike things cannot interact, to put it roughly. So magnetic fields can't act on currents. Rather, currents act directly on other currents. So you need to have two things of the same type or same character in order to interact. Faraday is saying, no, what's happening here is one magnet is producing a magnetic field, and that magnetic field in turn is acting on another magnet. This is quite a new conception of action at a distance, reducing it to a phenomenon of the same kind as that action at a distance which is extended by means of the tension of ropes and the pressure of rods. When the muscles of our bodies are excited by the stimulus which we are able to some unknown way to apply to them, the fibers tend to shorten themselves and at the same time to expand laterally. So think about your arm when you flex your bicep muscle. He's saying you don't quite know exactly how you do that. Sure, it's electrical signals, but how does it go from your will to creating that electrical signal? That's a mystery. But in any case, even if you don't understand exactly how the will connects with that electrical signal that goes to your muscle, when that muscle is excited, it shortens and it bulges. And by that method, it draws two bones closer together, for example. He says, when the muscles of our bodies are excited by the stimulus which we are able in some unknown way to apply to them, the fibers tend to shorten themselves and at the same time to expand laterally. A state of stress is produced in the muscle and the limb moves. This explanation of muscular action is by no means complete. It gives no account of the cause of the excitement of the state of stress, nor does it even investigate those forces of cohesion which enable the muscles to support the stress. Nevertheless, the simple fact that it substitutes as a kind of action which extends continuously along a material substance from one of which we know only a cause and an effect at a distance from each other induces us to accept it as a real addition to our knowledge of animal mechanism. And this is an analogy he's using. So he's likening these magnetic fields to a muscle connecting two things. For similar reasons, we may regard Faraday's conception of a state of stress in the electromagnetic field as a method of explaining action at a distance by means of the continuous transmission of force, even though we do not know how the state of stress is produced. But one of Faraday's most pregnant discoveries, that of the magnetic rotation of polarized light, what's now known as Faraday rotation, we talked a little bit about that in the context of reading John Tyndall. The rotation of polarized light enables us to proceed a step farther. The phenomenon, when analyzed into its simplest elements, may be described thus. Of two circularly polarized rays of light, precisely similar in configuration, but rotating in opposite directions, that ray is propagated with the greatest velocity, which rotates in the same direction as the electricity of the magnetizing current. So what is he saying here? There's a couple ways of understanding Faraday rotation. The way that he's describing it here is that if you have some material, and Faraday used heavy glass, and he passed a ray of light through the heavy glass, and if you have a magnetic field inside of the glass produced by an electrical current going through a wire. So let's suppose that we have an electrical current going in like this. The current is going around in this direction and coming out like this. If you have a ray of light going through, the way we talked about it is that the ray of light, if it's initially linearly polarized, the ray of light will begin to rotate its plane of polarization as it's going through. That's one way of understanding Faraday rotation. Another way is by saying, as Maxwell does here, if you have light that is circularly polarized, that means the polarization is already spinning. As it's going down here, the plane of polarization is spinning as it's going through this. So you've created somehow, maybe with a quarter wave plate, created circularly polarized light. If the rotation happens to be in the same direction that the current is going around that bar, then that light ray will travel at a high velocity. But if on the other hand, so this one that I've drawn here will be a high velocity ray of light. But on the other hand, if we were to pass a ray of light through there that was polarized so that it was rotating in the opposite direction, so it was polarized, it was undergoing circular polarization in this way, then, and if that is in the opposite direction that the electrical current going around the glass rod is flowing, then that would be traveling more slowly through the glass rod. So this is something that Faraday had studied, and one of the interesting things about this is that it led him to think that there was a connection between polarization of light and magnetic fields. So there is some magnetic property of light, and that leads Maxwell and Faraday to the concept of the electromagnetic theory of light. It follows from this, as Sir William Thomson, that's Lord Kelvin of the Kelvin temperature scale, Sir William Thomson has shown by strict dynamical reasoning that the medium, when under the action of magnetic force, must be in a state of rotation. That is to say, that small portions of the medium, which we may call molecular vortices, are rotating, each on its own axis, the direction of this axis being that of the magnetic force. So this is a little bit of an older way. This is not the modern way of looking at this, but the idea is that this medium, this glass rod in this case, it's got a magnetic field, but they're trying to understand this in terms of a kind of a spinning of the molecular properties of that glass rod. This magnetic field is causing some rotation in the medium that is acting on the light. Here then we have an explanation of the tendency of the lines of magnetic force to spread out laterally and to shorten themselves. It arises from the centrifugal force of the molecular vortices. The mode in which electromotive force acts in starting and stopping the vortices is more abstruse, difficult to understand, though it is of course consistent with dynamical principles. We have thus found that there are several different kinds of work to be done by the electromagnetic medium, if it exists. We have also seen that magnetism has an intimate relationship to light, and we know that there is a theory of light which supposes it to consist of the vibrations of a medium. How is this luminiferous medium related to our electromagnetic medium? It fortunately happens that electromagnetic measurements have been made from which we can calculate by dynamical principles the velocity of the propagation of small magnetic disturbances in the supposed electromagnetic medium. So what Maxwell's been doing here is been motivating this connection between electricity and magnetism on the one hand and light on the other. And now he's going to talk about the specific measurements of the speed of light and how they relate to his theoretical prediction of the speed that a disturbance of this electromagnetic field will travel. And we'll talk about that next time.